architect who is working on our building right now. Okay? So he brought some of his plans with us as well as a model. He's going to be presenting about how he uses similar triangles and similar shapes in his profession. So what I need for you guys right now is to clear off your desks, put food away, okay? And give him your undivided attention. If you're worried about homework, we will turn that all in tomorrow. Okay?
All right, thank you. So I'll be talking a little bit about how we use math in the production of this building or in creating this building, but also I wanted to give you guys kind of an overview of the process and how we actually came to the point where we are out there right now. So I brought a couple of volumes of the construction documents. These are the documents that the contractor's actually using to build the school. And so if you want to thumb through them, pass them around while I'm talking, that's great. Also, one of the tools that we have in our office to actually study proportion is a 3D printer. So we create models to get more of a visual of what the massing and the shape of the structure is going to be. This actually is of Logan High. This is what we're calling a classroom pod right here, this one little piece. So you can also pass that around and take a look at it. The top comes off, so don't feel like you broke it. If you can look inside. Okay, so just to introduce a little bit of the team that it takes to put a building together like Logan High School. Here I am. I'm my title, so to speak, team leader with MHTN Architects. We're out of Salt Lake City. You'll note what I want you to notice here is I have a group of consultants here. And these consultants actually they're not part of the MHTN company. They're separate companies, and they have specialties. I have a mechanical engineer, so he works on all of the air conditioning, heating, cooling, calculations, thermal calculations of the building, all those kinds of things. That's his expertise. I don't have that expertise, so I hire someone that has that expertise. I have an electrical engineer with the same expertise. He does the lighting calcs, make sure there's the right amount of lighting in the classrooms. He does the sound systems. And so again, he has that expertise. I have a structural engineer. Here's where math really comes into play. All of us use math, but the structural engineer, obviously doing math all the time, he calculates the building. He makes sure the building's going to stand up in an earthquake or just day to day. So he's also a consultant that I rely on heavily. And then I have a civil engineer. He does all the site work, the grading, and we'll get into a little bit of more of what each of those do. So one of the things that I've been doing for the last about 2 years is walking through Logan High School, investigating the existing condition. I need to get to know every corner, every piece, the structure, how it's built. And one of the things that I've noticed in almost every classroom, if not all classroom, is the 4 C's of Logan High School. How many of you are familiar with this or have been? Okay, almost everyone, great. So when I saw this, I immediately fell in love with it because communication, collaboration, critical thinking, those are skills that architects, engineers, we use every day. If we don't use those skills, we're in trouble. We have to have those skills. When I first started going to architecture school, I thought, oh, this is going to be awesome. I'm going to graduate from school, then I'm going to go work at my desk and create these awesome things all by myself, and then everybody's going to think that I'm so cool I created this awesome thing. Well, I found out quickly it doesn't work that way. Collaboration is a huge part of architecture. You've got, like I mentioned with my consultants, they all have an expertise that I don't have, and they bring it to the table, and we have to collaborate. I have to know enough about their expertise to collaborate and work with them, but I rely on them heavily. Just wanted to focus in on critical thinking for just a moment. I think it relates well to math, but also, so what is critical thinking? The mental process of actively and skillfully conceptualizing, applying, analyzing, synthesizing, and evaluating information. In other words, you're taking a bunch of information, you're thinking about it, and you're trying to come up with the best solution or an idea. I really like this quote from Daniel T. Willingham. It kind of puts critical thinking into context. Critical thinking is not a set of skills that can be deployed at any time in any context. It's a type of thought that even a 3-year-old can engage, even trained scientists can fail in. And it's very much dependent on domain knowledge and practice. So as we think about critical thinking, let me throw out a question. Why do you think critical thinking is so much dependent on domain knowledge? Anybody have an idea? It's pretty simple. The more you know, the more you're able to think about the things that you know. If I want to think about a structural problem, but I don't know anything about structures, I'm not going to be able to critically think about that very well. And so that domain knowledge is very critical to being able to think critically and solve problems. And today's workplace, solving problems is what employers want. They want people who can come in and think critically and solve problems. So like I said, a lot of employers, they're looking for people who can collaborate, communicate, think critically. And that's what's so great about what they're teaching here at Logan High, is developing those skills will pay off a lot in the future. So if you don't get anything else out of this presentation, remember the 4 C's, okay? And how important, I can't emphasize enough your future, how much that will help you if you can develop those skills. This actually is a picture of our office. You can see collaborating. This is the president of our company, Peggy McDonough. And this is a frequent occurrence in our office, sitting around, collaborating, talking about projects. Okay, I think we already hit that. Okay, so this one I'm going to demand someone raise their hand and take at least a guess, okay? So here's a little structures question. A hole or a notch for a pipe must be provided in a reinforced concrete beam. Which of the diagrams below shows the hole or notch that will least affect the beam's load carrying capacity? So what you have here, these arrows, just picture those as 2 columns or supports and the beam. So who'd like to take a guess?
B.
B, okay. Anybody else?
C.
C? Okay, tell me why B. Why do you think?
It's a bigger hole.
It's a bigger hole? Okay. And why C? Just a wild guess? Okay. Anybody else have a guess? Yeah, go ahead.
I'm gonna say D.
D?
If you think of least effect on the beam's load carrying capacity, it would have the most tension in the middle, right? So you want to reinforce the middle as much as you can rather than the ends. So as D is holding together the sides, it's
Right.
the middle the most.
Okay. You know what? That is an excellent guess. And that's critical thinking right there. You talked about tension, and you're absolutely right. Tension in the beam is occurring most in the middle. Now, the interesting thing about this is tension is on the bottom of the beam. What's on the top of the beam? Compression, yeah. The top is in compression and the bottom is in tension. Now there's two basic forces that are acting on this beam. Bending force, which we've talked about, compression and tension, and then shear force, which we haven't talked about yet. Any ideas on what shear force might be or how it's acting on that beam?
Shear force is kind of just like a really fast impact. It comes and goes really quickly, and it's a lot of force.
Okay, great. Yeah, that's exactly right. Shear force, kind of think of it as gravity or a force trying to push something apart or to break. Shear force on this beam is actually at its greatest point right at the edge of the columns, okay? And so you have compression in the top, tension in the bottom, and a great amount of shear force on each end. Think of that shear force as this beam is transferring load, and the closer it gets to the column, the more load it's gathering, and so the more shear, the more it wants to break off that beam. So now knowing that, let's think about this a little bit more. You've got compression, tension, and shear on the ends. Anybody want to take another guess?
Is this like a side view or top?
This is like a section view. So it's like an elevation. You're looking at it. This is the beam. If you're standing on the ground and you're looking like this, this is the beam. That's the concrete beam. And these arrows would be columns. Does that help? Good question. Yeah. Who wants to take another guess? I'll give you a hint. Nobody's guessed right yet. A. Correct. Okay. But there was some great thinking going on. A. And who wants to tell me why? Why A? It's in the middle, right? Yeah. You've got compression here, tension here. So in the middle, your bending force is the least amount. And of course on the ends, so if you notch it here, you're in tension, that's a bad spot to notch the beam. If you're up here at the top, you're in compression, that's not a great place to put a hole in the beam. If you're on the end, that's where shear is the greatest, so that's not a great place. Here you have the least amount of shear, and you also have the least amount of bending stress, okay? Great. So let's put it into practice a little bit. These are two details that are pulled directly from the construction document set that's going around. This is a detail that my structural engineer drew and detailed for the project. Now this is that beam, same view in elevation. So if I'm standing, I'm looking at it. That's the beam. This view here is in section. This view is in section. So if I were to take that beam and cut it in half, that's what I would see. This is also an elevation view. So it's actually two different details. This detail, elevation and section, and this detail with elevation and section, okay? So this is a typical opening in a beam. So the contractor has to follow this. Anytime he wants to cut a hole in a beam, this is the detail he's got to do. So let's take a look at this first. How many of you are familiar with the term wide flange? Wide flange beam. Anyone? Basically, it's an I-beam. You're familiar with the term I-beam? It's the beams that you're seeing going out there that all shaped like an I, okay? Steel beams. So this is a steel beam detail here. And there's the I shape right there. If you're able to cut it in half, that's the shape of the beam. So when I cut this one, you can see what the structural engineer is actually asking the contractor to do is add more horizontal pieces at the top and the bottom of that beam, right above the opening and right below the opening. And he's also asking for them to extend those pieces a certain distance. Anyone want to take a guess as to why he's having them add these additional pieces. We just talked about it. Yeah.
Extra reinforcement?
Reinforcement, exactly, yeah. So even though that hole is in the middle of the beam, it's still taking up a good portion of that beam, right? And so these pieces are actually helping on the top in compression and on the bottom in tension. It's reinforcing, reinforcing that opening so that it takes care of that compression and tension problem. It's also got notes about these openings. They can only go in certain places. If there's heavy loads, you can't put an opening. So anyway, here's another detail. Who can tell me or would like to take a guess? I'm going to ask a question. Why do they put rebar? First of all, do you guys know what rebar is? It's in concrete, the metal dowels that go in concrete. Can anybody tell me why they put that in concrete? Why rebar in concrete? Why not just poured concrete?
So earthquakes don't like destroy the building so that the walls can flex?
Yeah, exactly. It strengthens the concrete. Now, building materials have different properties, right? Concrete acts very good in compression. It's got very good compression strength. If you're to test the compression strength of concrete, it's very high, performed very well. But guess what? If you put concrete in tension, not very good. It'll crack and break. That's why you see cracks and breaks in your sidewalks, because when the earth moves, it puts that concrete in tension, and then you get a crack in your concrete, okay? But steel is excellent in tension, okay? And so that's why they put steel in concrete. It's the best of both worlds. You get the good compressive strength of concrete, you get the good tension strength of steel. Notice the steel here is where in the concrete? On the bottom, where it's in tension, okay? Okay, so I'm gonna admit right away that I don't do any of this stuff my job, but I have a structural engineer that does this all the time. So I had to brush up on this, okay? But one of the things to become an architect, you have to take 7 exams. Mechanical exam, a structural exam, and 5 others that are not fun. But anyway, I pulled this straight from the study guide for the structural exam for architects, okay? So this is talking about forces, resolving forces. And I'm not going to go through the entire problem, but essentially, if I have a force that is 1,300 pounds going in this direction at 23 degrees, how do you think we might be able to solve that? If we want to find out what the force is in the 2 X and Y direction. So essentially, what I'm trying to say, I don't think I'm explaining it very well, is structural engineers, they have to calculate forces that are going to be on the building, for example, an earthquake. The best way, lots of times the best way for them to calculate those forces might be coming in at a strange angle, but the best way for them to evaluate those on a building is actually separate those forces out into an X and a Y direction, and then they test that against the building in both directions. And so what they do is they take this force that may be coming at the building in any direction, and they separate it into an X and a Y force that would have the same effect on the building. And so it's quite simple. I'm sure if you're in this math class, you've all seen this before. A squared plus B squared equals C squared, Pythagorean theorem. So essentially, you can come to get the forces here. And so that becomes, this is like basic. This is first chapter of the study guide in my structural exam review information. So it gets way over my head from this point. So anyway, I just thought you'd find that interesting. Here's another piece where essentially you've got all these forces coming out of the same point, and the question is, if I were to add all those forces up, what direction would one force be, and what would be its magnitude, or how much is it? And so what you do is you add up you figure out all your x and y forces for each of those forces. You get your forces in the x, your forces in the y, and then essentially you can you add those up, sum of those forces, and then you use the tangent of the sum of the forces. You guys probably know this stuff better than I do. Like I said, I brushed up on this right before I came, and I'm sure that your teacher's going to review that with you and maybe even test you on it. Who knows? But anyway, that, you can probably tell by the way I'm talking about it, that's not my expertise. That's my structural engineer's expertise. But he uses it every day. I call him on the phone probably 2 or 3 times a week. He's a math genius, okay? So this here is a structural model of what's being built out there right now. This is what we're calling phase 1. So you can see just outside the admin office, all this steel has started to come up. Kind of orient yourselves, and a lot of this steel is already up. So they're working on filling in the gap right here. This is pulled from a computer program that our structural engineer uses to analyze the building if it were under an earthquake. And you can see these dark red pieces here. These are called moment frames. They help resist forces in this direction. And see, he has moment frames in the X direction and in the Y direction, of course. The building's got to be able to resist those forces in both directions. There we go. So this, again, is his computer program. And essentially, he's simulating an earthquake. And he's able to use this program to evaluate the building under the condition of an earthquake. So here's a little video. Okay, so that was in one direction. Here's another view. So they tested in both directions, as we've been talking about.
So what would happen to the structure if he didn't have those red beams to mitigate that force?
The moment frame, the structure would fall and crumble. It would break at the weakest point and start to come down.
Kind of like a domino reaction?
So earthquakes, as you all know, are very unpredictable, and it's difficult to predict what would happen. You know, it could be swaying like this and all of a sudden just snap and then just go like a pancake. I mean, it could do anything really. It's difficult to predict. I'm not an expert in knowing and predicting what those things are. My guess would be the earthquake starts to shake the building like this. It's going to be at its weakest point when it's pushing and putting all those forces at either this end or this end, and then it's just going to break and tip right over. Now, that video, so you know, was exaggerated. The building's not actually going to move that much in an earthquake, so it's exaggerated so that he can, the engineer can see the problem areas. How much do you think? Just take a wild guess. How much do you think that if the building is here how much do you think the top of that building, our structural engineer has calculated for it to move in an earthquake? What do you think the movement might be?
5 feet.
5 feet? Okay, that's a good guess. Any other guesses? I'll give you a clue. Less.
1 foot.
Less.
6 inches.
What's that? A little more than an inch. 3 inches. Okay, so that was exaggerated quite a bit. It's actually only moving 3 inches. Okay, so one of the things that we've done, the old building, there's a gap that's actually technically 2 buildings. You'll have your new building and the older one. And the reason why it's technically 2 buildings is there's a 5-inch gap between the old and the new that we've built in, because there's 3 inches there for the new building to move and 2 inches there for the old building to move, because in an earthquake, the last thing you want is this building doing this and the next building right over doing this and them hitting each other. So that happens sometimes in earthquakes if those kinds of things aren't calculated. Okay, who recognizes this? Raise your hand if you've seen this before. Anybody? What's that?
Looks like the UIU in 1899.
Okay.
Just a little label.
Guess where that building is? Right here, yep. How many of you knew that? Yep. Brigham Young College. Logan High started out as Brigham Young College, and this building used to sit. So the tower that you've seen all getting built right outside, this tower was about 30 feet from where that tower is being built, okay? One of the things that was very important to the district was that the new architecture of Logan High School have a sense of community, a sense of history. And so we went back and we looked at the history of this site and what's gone on in this site. And quite frankly, Logan High School is an incredibly special place. There's not a lot of high schools in the state where their history goes clear back into the 1800s. Pretty awesome. My wife is a Logan High graduate, and she had no idea. I had no idea till I started working on this project, and I grew up in the valley also. Okay, here's another structural problem. Let's see, how are we doing on time? 10 minutes? Okay. So you've seen the renderings, the towers going up. My structural engineer comes to me one day and he sends me this email and he says, I've got 4 options on how we can frame this tower. Here's the 4 options, what do you think? So here's 2 of the options. He's saying, you know, we can take this 2 wide flanges. Okay, I've got 4 options, these are 2 of them. I can take this wide flange beam, I can cut one of them right in half, and I can create this kind of crossing shape beam. Now, one of the reasons why we need to do something tricky like this is the structure, the tower also needed to be its own building. So it's got to be able to resist forces in both directions. And so these beams are strongest in resisting forces in this shape here. So you've got to have that shape in both directions so that you can resist the forces in both directions. So there's one. Here's another one. Well, let's just take 2 beams and nest them one inside the other. Okay. Option number 3. Well, let's just make it out of concrete and put a bunch of rebar in it. Or option number 4, let's do 3 little columns and put steel plates on them, and these steel plates will help resist the forces in both directions. So, my structural engineer calls me, gives me these 4 options. What do you want to do? I'll do whatever you want to do. What do you guys think my next move ought to be? What's that? Don't know.
Find out which one's the safest.
Find out, okay, which one's the safest, that's good. Okay, I find out they're all equally safe. They can all be done equally safe. Then what do I do? Yeah,
Find the cheapest one.
cheapest one, yeah. That's a good idea. Let's cost it out and see which one's gonna cost more or less, okay? And that actually, now, I don't want you to think that cost drives everything, but of course it's a factor when you're building a project, okay? So that's what we did. I called up, you're starting to probably catch the theme here. There's a lot of experts and I delegate to the experts. So I called up the cost estimator on the project and I said, can you take a look at these 4 options? What do you think? And so, of course, there's math in his takeoff. He had to figure out how much steel was in each column. And then steel is priced by weight. And so he's calculating all that, putting the cost together. And option 1, well, one other thing before I go through that is, one of the nice things he did is there's a lot of things about this tower that are going to be the same on all 4 options. And so he didn't take the time to cost out all those things that are the same, like the brick. It's going to be the same on all 4 options. But what he costed out were the things that were going to be different. The top of the tower was going to be the same on all 4 options. So he just separated that piece that was the variable, or the part that was changing, and gave us a cost estimate for that piece. So option 1, 72,000. Option 2, right there at 72,000. He says there's a few less welds on option 2, so it'll be a little less. Option 3, the concrete option, $120,000. Option 4, $54,875. Okay, so option 4 wins in the cost analysis, but do you think, are we done yet? Is cost the only? No, that's right. The other thing I have to evaluate is, okay, is this shape of this column going to work with the building? Is the architecture going to be able to work around it? And this 3-column piece ended up being a little bit larger than some of the other shapes would have been. And we had to modify our detail to make that shape work. So part of the process was, okay, can we use this shape? I think we can. Let's look at it. We can really save the district some money if we can get this shape to work. And we were able to do that. We were able to save the district some money and modify our detail. And the important thing to us was we wanted this 4-foot dimension, which is, by the way, this is, if I were to take the leg of one of those tower columns and chop it and look straight down at it, that's what you would be looking at, okay? And so that 4-foot dimension of that column was important to us because it's the proportion or the size of that column that made the tower look the best. Have you ever seen a house, and this drives me crazy, but have you ever seen a house with a small little canopy and big huge columns? Look a little goofy? Yeah. So proportion's very important to us, you know, and a lot of it is experience and training, just being able to see the right proportion. So we've got 5 minutes. Okay, I'm going to stop right there and give you guys the opportunity to ask me questions. Any questions you want.
When is it supposed to be done?
When is it supposed to be done? I thought that question was coming. Okay, so there's 2 phases. They're working on phase 1 right now, and phase 1 is about half of the new building. Phase 1 will be done next summer. So next year, you'll all get to use half of the new building. Phase 2 will then be built during that following year, and will open up fall of 2017. So you'll be done in 2017. Yeah.
So is that going to be connected to
Is what?
is that new building going to be connected to our school?
Yes. Yeah. So
That we're standing in right now isn't gonna be here next year.
Yep, this building gets demolished next summer. So I see where you might be going there. There's that 5-inch expansion joint. How do you cover that up? Well, there's special architectural details and things you can do to, have you ever walked across the floor and you see a big metal plate going all the way across the floor? That's probably an expansion joint cover. There's probably a gap under that plate, and that plate allows the buildings to move, but makes it so that you can walk across that gap.
When you're done, how much of the original school before you start working on this subdivision?
Say that again?
Sorry. When you're done working on 2017, how much of like the original school is still going to be here?
Okay. So the question was, how much of the original school will still be here when we're all done in 2017? The English wing is going to get demolished. This entire admin building will get demolished. So what's going to stay is the media center, the auditorium, the gym. In fact, let me skip ahead here. Okay, so here's a good diagram. Here's phase 1. It's getting built right now. There's the tower right there, part of phase 1, right on the edge. There's phase 2. So you can see, got your gym, your auditorium, and then kind of, I don't know what, we call this the old girls' gym wing. It used to be a girls' gym. And then you've got your 92 edition that's all staying, the south classroom wing. And then the media center portion will stay as well. We'll interface that with phase 2. And so we've already demolished the CTE wing. We've already demolished your front entry commons. This building comes down and the English wing comes down. No, the stage will not get torn down. The auditorium's staying. However, the auditorium's going to be completely remodeled, okay? One of the things that's going on right now is taking the roof off the auditorium, and the auditorium doesn't meet current seismic codes or earthquake codes. And so we're bringing that all up to date so that if an earthquake does hit the auditorium, you'll be safe. But a complete remodel, new sound system, new finishes. It's going to be an awesome auditorium.
Will the parking lot be done with phase 1 or phase 2?
Parking. How did I know someone was going to ask about parking? So portions of the parking lot will be done in phase 1. Most of the parking lot is phase 2. So parking is we understand parking is very limited here, and it's a delicate balance of the space the contractor needs to build the project and providing as much parking as possible for the students and faculty to be able to park. Parking has never been fun at Logan High. That's what the superintendent has said. So at the end of the day, we'll have more parking than what you started with.
Thank you
So,
very much. Appreciate your time.
thanks guys.